Hello everyone. Welcome back to the video lecture series on geotechnical engineering with me, Nihal Naveen. In the previous video, we did shallow foundation part 5, and in that we started with the plate load test, okay? And it is a field method test. In this video, we are going to start the standard penetration test, and we'll also solve some numericals from previous year GATE and engineering services exam, okay? So this will be the last portion of shallow foundation. I hope you will enjoy it. So let's begin. Shallow foundation part 6. Standard penetration test. Okay. Now this standard penetration test, it can be used to determine a number of values. The first is the relative density of sand, that is ID. Okay. You have studied about the relative density of sand. Second is the angle of internal friction, that is phi value. The third is the unconfined compressive strength in case of clay, that is QU. Okay. Unconfined, in the unconfined state, okay, when sigma 3 is not acting, that is sigma 3 or sigma c is not acting. You have studied this in case of triaxial test. Fourth is the ultimate bearing capacity, okay, that is UBC or denoted by QU, okay. Actually ultimate bearing capacity is also denoted by QU only. Allowable bearing pressure, okay, that is QAP. This is based on settlement criteria, as you already know, and ultimate bearing capacity is dependent on the shear criteria. Now you can also calculate the load carrying capacity of piles. Pile is a type of deep foundation. You will be studying this in the next video. What is the deep foundation? Okay. So let's see the procedure of standard penetration test. And this test is generally asked in the different competitive exams. Okay. You have some correction factors as well. You have to keep in mind all those. Okay. So let's see the procedure. This is actually the whole apparatus of standard penetration test. It is conducted at regular intervals of 2 to 5 meter or when stratum is changing. Okay. Here what happens, first a borehole is made up to depth at which SPT number, that is standard penetration number, has to be calculated. For example, if you have to find the standard penetration number here, then you have to make a bore hole, okay, at up to this depth, okay. Then you have to enter this. This is called the split spoon sampler, okay, split spoon sampler. Now this is used to penetrate the soil by applying some impact from above, and to give some impact we have this hammer, okay, standard hammer. Its weight is 65 kg and it is this height at which it is dropped, it is around 75 centimeter, okay, or 30 inch you may say, okay. So this is the height from which hammer is dropped using this pulley structure, okay, and impact is applied, and you will find that there is penetration in the sampler, okay. There will be penetration in the soil. And what do you mean by standard penetration number? Actually, it is actually defined as the number of blows, okay, number of blows required for 300 millimeter penetration of this split spoon sampler. Now this whole procedure, it is done in 3 stages, okay, that is at 150 millimeter penetration each. Now we discard this 150 millimeter, the first 150 millimeter, okay, because it is the seating drive. We discard this first 150 millimeter value and we take the next two 150 millimeter values, that is 150 plus 150, it will become 300. So this number of blows which is required to do a penetration of 300 millimeter using the split spoon sampler, that is known as the standard penetration number, okay, or SPT number denoted by capital N, okay. Now this SPT number is related to, when we have calculated the SPT number and then we perform the corrections, that is the dilatancy correction and the overburden correction, after then we get the final SPT value, and that SPT value is actually related to the internal friction angle. And we already know that once we find the internal friction angle, we can calculate the bearing capacity factor of Terzaghi, okay, and from that you can obtain the NC, NQ and N5 values and gamma values, okay, which are used to find the ultimate bearing capacity, that is QU, using Terzaghi's equation, that is CNC plus QNQ plus half gamma PN gamma, okay. So as you obtain the value of phi, you get NC, NQ and gamma values, and naturally you can get the value of QU. So you can get the value of ultimate bearing capacity indirectly using conducting this standard penetration test. Okay. Now let's see the corrections which occur in standard penetration test. First, as I told, is the overburden correction. Now what happens actually when we are performing this test in the shallow level, that is in the upper space, we find that there is less confinement, okay, because overburden pressure is less. So SPT value naturally will be less because less number of blows will be required to compress this, penetrate this 300 millimeter. But at greater depths there is more confinement. So we have more overburden pressure and naturally we have higher penetration resistance at the greater depths. So the value increases of SPT increases at a greater depth. So we have to make some correction on this N value that we have obtained naturally. That's the observed value of SPT. It is denoted by N0 and the correction is N1 is equal to N0 into 350 by sigma bar plus 70. Now this sigma bar is actually the overburden effective stress, okay, that is gamma dF, okay, and this value has to be less than 280 kilonewton per meter square. You have to keep this in mind because sometimes in question will be given this value is 300 kilonewton per meter square effective stress, you get it, okay. So naturally this will be 350 by 370, so this value will decrease. So this is not possible actually. When this value is greater than 280 kilonewton per meter square, then we don't have to perform this overburden correction with SPT. Okay, just remember this. The value has to be less than 280 kilonewton per meter square. So just remember this formula. N1 is equal to N0 into 350 by effective stress plus 70. Now after performing this overburden correction, we have to use this N1 value to find the dilatancy correction. Okay, and this formula is given as N2 is equal to 15 plus half of N1 minus 15. Now this is only used when N1 value is greater than 15. Okay, why? Because when N1 is greater than 15, it indicates a dense sand, okay, which on repeated blows gives a pore water pressure. Now this pore water pressure causes dilation effect, that is negative pore water pressure is produced here, and so we have to apply this correction factor here. Okay, so N2 is the corrected SPT for water table and N1 is the corrected SPT for overburden. Now generally people commit the mistakes here. If they have to find a dilatancy correction, we have to find the final SPT value. They directly put the value of N0 here sometimes. Okay, N0 is the observed value. From observed value you have to find first you have to apply first the overburden correction and obtain the N1 value, and then using N1 value you have to find the N2 value. Okay, that will be the final corrected value. Okay, and it will be applied only when N1 is greater than 15. Why? Because this value will become negative. Okay, so this is applied after overburden correction in fine sand or silt. So this is applied only on fine sand or silt. Now let's take a note here. If the test is conducted at different levels, now we are conducting this test at different levels, let's say A, B, C and D, then the final SPT number we have to find. That will be the average of all these corrected values. First you have to make the correction and obtain the N value, that is corrected N value, then we have to find the average of all these corrected values. Okay, that is NA plus NB plus NC plus ND by 4, because there are 4 levels. Now if any of this corrected value we have obtained, that is NA, NB, NC or ND, it is either in the positive or negative 50% variation, then we have to discard that value. Okay, we have to discard that value if there is more than 50% variation from the average. So let's take an illustration. You will understand this better, what we have to discard and what we have to take. Let this SPT test conducted at 4 levels with values as 30, 32, 60 and 34. Now 4 values of SPT and value is given. Now these are corrected values. Now find the final SPT value. How we will find it? Firstly we will find the average value, that is NA plus NB plus NC plus ND by 4, that is 30 plus 32 plus 60 plus 34 by 4. This will give the value as 39. Okay. Now we will take 50% variation of this, both in the positive and negative side. Now what will be the negative side? We will take 0.5 times of this N value. it will be 39 into 0.5. That value is 19.5. And we will take 50% variation on the positive side, that is 1.5 times of n. So 39 into 1.5. This value we will obtain as 58.5. So all these corrected values have to lie in the range of 19.5 to 58.5. Now if any value is beyond this range, we have to discard that value. That is the meaning of this statement. Okay. So you naturally find that this 60, it is lying above this range. Okay. So you have to discard this value. So we will take just these three values, that is 30 plus 32 plus 34 divided by 3. Okay. So we will get this final value as 32. So as final SPT n value is 32. Okay, you have to keep this in mind how to calculate this. Now this another field test is there, that is static cone penetration test. Okay, SCPT. Okay, that was SPT, and here S stands for standard, here S stands for static. Okay, static cone penetration test, don't confuse. Now this is generally used for soft cohesive deposits, generally soft clays. Okay, you have to remember this. Now you don't have to go in detail of this static cone penetration test from the gate point of view. Just read some of the important concept of this. In soft soil, SPT value is likely to get affected by speed of hammer. Okay, naturally we know when there is a soft soil, then we go on the speed of hammer, that is the blow at which, the rate of blow at which we are giving. That will also affect the SPT value in case of loose soils. So static cone test is performed here. Now this is the apparatus actually. Okay, and cone is pushed 80 millimeter into this soil, 80 mm at a depth of 80 millimeter with a uniform rate of 15 to 20 millimeter per second. Okay, by means of this the inner rod. Okay, and by means of inner rod you have to give the penetration, and the end resistance of cone at any depth is called the cone penetration resistance. Okay, just go through this. If you want to go in great detail, then you can consult a standard book. You will get it. Standard cone penetration test, static cone penetration test. Okay. Now coming to the next concept, there is a settlement distribution and contact pressure. Now this is generally asked in the GATE and ES exams continuously. They go on asking every 2 or 3 years. Now what is this concept? You have to actually find there are 4 cases in this: flexible foundation and rigid foundation, both for clayey and sandy soil. Now let's take it one by one. First for clayey soil. Okay, for clay. First we will go for flexible footing. Now what happens in case of flexible footing? The contact pressure, that is the pressure which is acting between the layers of the footing and the soil, that is uniformly distributed. Okay, this is actually the flexible footing. Okay, flexible footing. So this contact pressure which is acting, this is uniformly distributed in case of flexible footing. Okay, so here what we observe, a uniform plate like dish shaped settlement occurs here in case of flexible footing over clayey soil. Okay, you have to remember this. You have to just keep in mind this figure. Now let's take the case of rigid footing. What happens in rigid footing? In rigid footing, settlement has to be uniform. Now here the settlement was dish shaped, but here as it is a rigid footing, so settlement has to be uniform. Now if the settlement has to be uniform, then there has to be change in the contact pressure. Now contact pressure will be like this. Why? Because here at the middle we had a dish shaped, so more settlement was here, so naturally we will require less contact pressure to balance. Okay, since flexible footing produces a dish shaped pattern in clay soil, okay, contact pressure must be more near the edge. So contact pressure here will be more but less at the center, so to balance it. Okay, so just remember this. First you have to keep this mind. In flexible footing, the contact pressure is uniformly distributed, and in case of rigid footing, the settlement is uniform, okay, over all the contact area. Now this was for clay. Now we will come for sand. Flexible footing over granular soil, that is sand. In granular soil like sand, modulus of elasticity, that's E value, it varies across the contact area, that is the width. Okay, it is maximum at the center and minimum at the edges. So when it is maximum at the center, what will happen? If modulus of elasticity value is maximum at the center, naturally the deflection will be less, okay, because it has more strength. So here we find that deflection is like this. Maximum at the edges because E value is minimum at the edges, and settlement is minimum at center. Why? Because we have maximum E value at the center. So you can just read this as E is max at center, deflection is less at center, and E is less at edge, so deflection is more at edge. Okay. Now the fourth case and the last case is rigid footing over granular soil. Okay. Now what happens in case of rigid footing? You already know settlement has to be uniform. Again, the settlement will be uniform in this case, and for this the contact pressure is more near the center. Here the contact pressure has to be more than the edges. Okay, edges we have less. So it forms more or less a parabolic type of contact pressure. Okay. So in flexible footing, here also you have uniformly distributed contact pressure. So just keep in mind 2 points as I told. In case of flexible footing, you have uniformly distributed contact pressure, but in case of rigid footing, you have uniform settlement. Okay. So naturally contact pressure and settlement will change accordingly. Just keep in mind these 4 figures. Okay. This is for flexible and this is for rigid. Okay. I hope this settlement distribution contact pressure is clear to all of you. Okay. Now let's take some numericals from previous year engineering services exam. This was asked in year 2009. Let's take the question. The standard penetration resistance value. Now it is asking standard penetration resistance value. So it is from SPT. Obtained a deep deposit of sand at a depth of 6 meter was 28. Now N value is given as 28. The unit weight of sand is 18 kN per meter cube. Gamma value is given as 18 kN per meter cube. What is the corrected value for the number of blows for overburden pressure? For overburden pressure, what we know? N1 is equal to N0 into 350 by sigma bar plus 70. Okay, so we have to first find this value of sigma bar. What is the value of sigma bar? This value will be gamma into df. Okay, you know this. Gamma value is given as 18 into depth of foundation is given as 6 meter. Okay, so this value is 108 kilonewton per meter square. Now as this value is less than 280, so we can consider this. Okay, so N1 will be N0 that we have the observed value is given as 28 into 350 by sigma bar, that is 108 plus 70. Okay, so this will be 178, and finally N1 value, that is after corrected for overburden pressure, we will obtain N1 value as 55. Okay, so the correct option is option D. Hope this is clear. And if dilatancy correction is given, you have to use this N1 value and use that formula for dilatancy correction. Okay, and it will only be used when N1 value has to be greater than 50. Now let's take this question from GATE from the year 2016. This is a very good question. Okay, let's see this. A 4 meter wide strip footing is founded at a depth of 1.5 meter below the ground surface. Now this depth of footing, it is given as df is given as 1.5 meter, and it is given that this 4 meter wide, that is B is given as width of footing is given as 4 meter. The water table is at a depth of 5.5 meter below the ground surface. So water table is present here at depth of 5.5 meter. The soil properties are C dash is equal to 35 kN per meter square. Cohesion value is given as 35 kN per meter square. Angle of internal friction is given as 28.63 degree. And unit weight, saturated unit weight you have 19 kN per meter cube. And bulk unit weight you have, that is below you have 19 and here you have 17 kN per meter cube. Okay, and unit weight of water is given as 9.81 kN per meter cube. The values of bearing capacity factors for different phi are given below. Now, according to the 5 values, you have NC, NQ and N gamma, that is the bearing capacity factor of Terzaghi, it is given. Now, what you have to find is using Terzaghi bearing capacity equation and a factor of safety 2.5. Now, factor of safety also is given. Now, naturally, no, this thing will come to your mind when factor of safety is given in the question. You have to find the safe bearing capacity. So it is asking the net safe bearing capacity. So you have to use both the QU net safe, okay, that is, first you will find QNU, that is net ultimate bearing capacity. It will be QU minus effective stress, okay, and then you will find the net safe bearing capacity, that is net QNS, that is QNU by FOS. So this only you have to find. Now you have to find just this value of QU and sigma bar. So for all these the values is given. Now you have to keep in mind this factor. For local shear failure of the soil, now it is given in question, this is a case of local shear failure. Many people will not see this. Firstly, they will just see the values and they will start solving the problem. They just don't read the question. Firstly, you have to focus and read on the question first. Even if it takes 1 minute, if you have spent that 1 minute, then you go on, proceed the solution, okay. Just don't miss any word. In once only you read the question fully, okay. Just don't miss any word. So here it is a case of local shear failure. So local shear failure, you already know you have to use the modified values of cohesion and phi. So Cm is equal to 2 by 3 times of C dash. That is given 2 by 3 times of C value. What is given? 35. So this value comes 23.33 kilonewton per meter square, okay. And phi m value, modified internal of friction, as tan phi m we have, okay, we have 2 by 3 times of tan of phi dash. Now phi dash angle it is given as tan of 28.63 degree, okay. Now phi m will be tan inverse of this, okay, so we'll use this. So we'll get this phi m as 20 degree, okay. So we have to use the NC, NQ and gamma values corresponding to this 20 degree, okay, not 28.66 degree. The students will directly go on interpolating. They will find the values of this. They will find the value 28.63 and the values will be lying between these two values. So they will commit this mistake. You have to see this. We have to find the modified phi value and correspondingly NC, NQ and gamma value. So we get these values as 17.7, 7.4 and 5. We will use these values, okay. So let's proceed. Now we know that QU is equal to CNC plus QNQ plus half gamma BN gamma, okay. Now C value we have got as 23.33. So 23.33 into NC value we have obtained 17.7, okay, plus Q is gamma into DF. Depth of foundation is 1.5, gamma is 17, because we will take bulk, because water table is present below, okay. Water table is 1.5 plus 4. Now shear zone is acting up to this, okay. The stress zone is present up to here. So naturally this water table will have no effect on this bearing capacity. So we don't need to consider any correction factor RW or RW dash. So 17 into depth of foundation, that is 1.5 into NQ. NQ value is 7.4, okay. So in the third part, that is half into gamma value, again 17 into B, width of foundation is given as 4, into N gamma we have obtained 5. So finally QU value we will obtain as, this value will be 771.64 kilonewton per meter square, okay. Now we have to find the net safe bearing capacity. Now QNU is equal to QU minus sigma effective, okay. QU we have obtained 771.64 minus gamma DF. Gamma is again 17 into depth of foundation 1.5. So this final value we will have 746.14 kilonewton per meter square, okay. I hope this is clear. Now we have to find the safe bearing capacity, net safe. So QNS is equal to QNU by FOS. So 746.14 by 2.5, and we will have the value as 298.48, okay, kilonewton per meter square. So this is the final result that we have obtained. So the answer will be 298.48 kilonewton per meter square. I hope this question has cleared your concept regarding this finding the net safe bearing capacity. I've already taken some questions in before as well, so just go through the previous videos. And we come to the end of this shallow foundation part. I hope all this part, the 6 parts, were quite clear to you. Just go through them and it will be really helpful for you in understanding the concept of shallow foundation, and you will directly, after watching these videos, you can directly go to the previous year books, and I hope you will be able to solve all the questions quite easily. Okay. Now in the next video we will be starting with the deep foundation, okay, that is the pile foundation, and it is also very important from the gate point of view. So don't miss those videos, just watch all the parts, and you can also practice free quizzes at Grade Up and always be a grade higher. Thank you and all the best.